So here's the Carnot cycle with pistons put on it. So at the hot isotherm, that's when we're pushing that gas. The gas is pushing the piston down. Adiabat, we kind of lose the ability to put heat into it because it's happening so fast. We've got some momentum to the engine, and it finishes out that stroke. So this is the full stroke. Volume is the minimum volume. Volume C is the maximum volume. And then this crank turns around and starts compressing the gas. We want to compress the gas as cold as possible. That makes it more efficient. And then we lose the ability to sink the heat of compression, and then it starts to heat the gas up, and we get back up to the hot. Okay. Now this is an idealized system. This is the Carnot cycle, but this is the actual Otto cycle for gas engines. And we have four-stroke engine. These are the 4 strokes. Okay, so we have this part here where we spark the spark plug, and it burns the gas, and we get a huge jump in temperature and a huge jump in pressure. So that's why we have this at the minimum volume, we have this explosion, and we see this violent explosion go up, and now we have a really hot gas that's able to push. Now, we're not able to effectively sink a lot of that heat, and so these are adiabatic expansions. We don't have any isotherms in the gasoline engine of adiabat. But anyway, if we see here, we're starting out E to C, that's the intake. So the piston is down here at its minimum volume, and we pull the piston down with this turning crank here, and look what's open here. This is the intake valve. So the fuel and the fuel and air mixture comes into the piston, but it's cold. It's at the cold temperature. It's at low pressure, like maybe not quite 1 atmosphere. Sometimes there's a vacuum in your engine when it's pulling, so it pulls that air and fuel in. Sometimes it's sprayed in with a fuel injector. But anyway, it comes in at a really low pressure and cold temperature. Cold could be 729 Kelvin. Cold could be 372 Kelvin. That's what we don't know. Okay. So it comes in, and then that valve shuts. Okay. And when that valve closes, then we start to compress. We close that intake valve, and that's 1 stroke. So that's the intake stroke, and then we have the compression stroke. So it starts to compress the gas as it's pushing up. You see, this is a stroke down, this is a stroke up. So it's going up and compressing the gas. When it gets here to the minimum volume, okay, that's compression. When it gets to the minimum volume, we spark the spark plug. Okay. So you see right here, a little spark plug burns, D to A, that's going up in pressure and temperature. And then we have the power stroke. So this is when it really shoves the engine. We fire the spark plug, we get a jump in pressure and temperature, and then we have this expansion, that's the power stroke. That's the only stroke that pushes the engine. We've burned the gas, and that's the only one that generates thrust. So in a 4-stroke engine, only one, the power stroke, is the one that's giving you a punch. Okay. So it pushes down really strongly, that's the power stroke. Okay. And then when we get to the bottom, look what happens. We open the exhaust port, this valve over here, so that the combustion gases can be pushed out. And so then we have the exhaust stroke. So it comes over here. If we open that exhaust valve, what happens when you open that valve is, boom, the pressure drops dramatically. And then we burn a whole stroke just pushing the exhaust out. So the piston does this. It sucks in, it compresses the gas, it explodes and gives you the power stroke, and then it exhausts the gas. So the intake and exhaust happen at this low pressure part. We suck in with the piston coming down, we go through the thing, and then we push the gas out by the piston going up. So we're just exchanging gas on the intake and exhaust strokes. And then 1 stroke is a compression stroke with the valves are closed and the explosion. And then you have the power stroke, the valves are still closed, so you can have that power. Now, we can make a 1-piston engine in here if we have a flywheel. The flywheel has to carry it past the intake and exhaust because there's no power being generated there. So you can have power, exhaust, intake, compression, power, exhaust, intake, compression. And those are the 4 strokes of a 4-stroke engine. And all our gasoline engines are 4-stroke. If you have a 2-stroke engine, it's a little bit more complicated. It's still a compression and an expansion, but there's constant flow in here where the air shoots in and the exhaust shoots out. Okay, good. Okay, so that's the four-stroke engine, and then out here we close that exhaust and open the intake and start over. So here's a little video that shows this going on.
A basic lesson in the fundamentals of a four-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every four-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A four-stroke engine is called a four-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion or 2 strokes of the piston to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many...
If you notice, it's hard to see, but if you came up here, you'd see there's a little rod there, and on that rod are some oval-shaped objects called cams. So when the thing is, so I'm spinning around like right here, so it comes around like that, and it causes that thing to rock up and down, and that's what pushes the valves open. Yeah, so that's the camshaft on top. And when you have like when you have 2 rows of those, we have dual overhead cams, DOHC. That was more efficient or something, or maybe better performance, I don't know. But sometimes you'll see that on engines or even on the backs of some sports cars, it'll say DOHC, and that's what it's standing for, dual overhead cams. Now that's a really important thing because the crankshaft is down here, the camshaft's on top. There's a timing belt that connects the two. Because if they get out of whack and they're trying to do a power stroke and one of the valves is open, all the gas is just going to blow out through the valve, the open valve, and not give you a power stroke, and your engine's not going to run. Yeah. Yeah, that's right. Yeah. And so your valves and your pistons weren't timed. And so if they're not timed, then the valves aren't open at the right time. So that's the timing belt. So anyway, this is now it's going through these revolutions per minute. So when you look on your engine and you see 2,000 RPMs, 2,000 cycles every minute, that's crazy fast. Yeah, yeah. So it's just so fast. 8,000 of those strokes going every minute. So you feel continuous power, but it's not continuous. It's individual explosions, but there's 8,000 every minute. So, it's better to have tiny little explosions and lots of them to get smooth power. Yeah. Now, sometimes, smaller engines, you can hear the individual explosions, and like a lawnmower is most lawnmowers are single piston engines that have a flywheel. And so you pull on it to get it started, and you're trying to get some intake, and you're trying to get a spark, and it pops, and it's enough to get it going. But if it's a cold engine, the gas doesn't have a good vapor pressure. You got plenty of air, but you don't have a lot of gas vapor, because it's cold. And it's the vapor that burns. So you don't have a good explosion, so you don't have a good power stroke, so it doesn't go all the way around to compress the gas. When it gets to the compression step, if it doesn't have enough energy, it'll stop. And so you pull it and it goes, it's going around a few times, but it doesn't have enough power stroke to get it through the compression step. And so that's why you always want to pull on the string to get it right up adjacent to the compression step, because that's where you want to, if you pull, sometimes you can get like 2 cycles for a pull of the rope if you're using a pull string thing. And so you get it right up next to the compression step. You can feel the resistance. That's the compression stroke. And then you let the little ratchet pull back down, and then you pull, and you can get at least 2 cycles of the engine with every pull, maybe 3. And that'll give it hopefully enough power stroke to kind of build itself up to a stable running state. So that's a pretty neat video. I can put the link to it online. So we've kind of gone through all that. Here's the diesel engine. So the Otto cycle, which is kind of funny, it's the name Otto, not AUTO, but it's funny because it's a homonym. Okay, the Otto cycle is a gasoline engine. This is a diesel engine. Okay, so we compress the gas, the fuel-air mixture up here, and then with the more modern diesels, we have a high-pressure rail, a high-pressure fuel rail, and direct injection. So really, instead of the intake valve, we have actual fuel injectors in the cylinder. So they're spraying the diesel in, and they start to spray it in at this really high thing, and the compression is such that there's enough oxygen and it's high pressure enough that the diesel will just start burning. All it needs is compression to ignite it. It's auto ignition at this high pressure. And they continue to spray some fuel in there, and they get this isobaric expansion. So we could calculate that with the number of moles times minus px times delta V. So this is not an isothermal expansion, this is an isobaric expansion. So we get a little bit more of a boost there. We hit this adiabat at a really high temperature. It drops down to the maximum volume. We open the exit exhaust valve, do the intake, and then we have the compression stroke. So because we get a higher pressure and higher temperature out of diesel, that increases our efficiency. So they run at a higher pressure, mainly it's the improvement in efficiency.
I think in a gas engine has these.
Well, because the gas engine doesn't get as high a pressure as the diesel engine, and so the diesel, it won't burn efficiently enough, and we're not directly injecting the diesel into the hot cylinder, so diesel doesn't have as much vapor pressure as gasoline. So we really, in a gas engine, we're depending upon the vapor pressure of the volatile gasoline. It's more volatile. That's why you don't ever want to use it to start a campfire or anything, because the gasoline is much more volatile. In fact, it'll follow you along the ground. A lot of people are burned every year trying to start a campfire or a burn pile with gasoline. They dump it all around, and the gas vapor's all over their clothes. They even take the jug way over here, but now they've got a trail of gas vapor, and they pitch something in there. They light it, pitch in there or whatever, and it flashes back at them, and it'll catch them on fire. So gasoline is very dangerous because it is so volatile, and diesel is much safer if you're going to use it to start a burn pile or something. But yeah, this is pretty much the same thing. You have the intake, compression, power, and exhaust. We just have a little bit different things. We have the intake is E to D. D to A is the compression, but the power A, B, and C. So here we're spraying that diesel in with a high pressure fuel rail, and then we have the power stroke, and then the exhaust. Again, open the exhaust valve and exhaust the gas. Here they are written on this diagram. Now we get into jet engines. These are really weird, okay? We have a compressor and a turbine that are running all the time. And so the air and fuel come in, actually the air is compressed and the fuel is sprayed into the combustion chamber. And then the hot combustion gases turn the power turbine, and the power turbine turns the compressor. So the front and the back are connected. So when they spin up a jet engine, it's not generating its own power at first. We're spinning it up with some sort of motor that turns the compressor, and then we light that fuel. And once that fuel starts to turn the turbine, then it compresses its own gas, like it's running itself. But we can adjust this by the pitch of the blades in a jet engine. So the compressor pitch blades are pitched a certain way to compress the gas, and then the turbine pitch blades are at a certain pitch to capture as much energy as possible. Now, on our military jets, we have what's called afterburners. And so then they put more fuel out here in the back with the exhaust, and it's like more like a rocket than a fuel. They're just spraying fuel out and creating thrust by putting fuel after the turbine. So it's not very efficient because they're just burning through tons of fuel, but it does give you an incredible boost. And so here's our picture of a modern turbine engine. Notice we have the pitch of the blades, but we also have a smaller volume. And so we're stuffing that gas into a smaller volume, and then we enter the combustion chamber where we spray in the fuel. And then we have this turbine that's capturing that expanding gas, hot expanding gas that's connected to the compressor to compress it more efficiently. And then it's making a hotter gas that's compressing it more efficiently. So this is a really great design of an engine, probably the most efficient engines that we have. And then we can take this front end here. We can put this on an airplane and use the thrust, to fly, or we could put this front end on a generator, and we could generate electricity straight from the combustion reaction. So at Roans Prairie, we have this kind of thing. So here's our airplane jet engine, okay, that burns natural gas, and it's connected to a generator. So it's a gas turbine power plant, which we have at Roans Prairie. You guys drive by that when you go to College Station?
Let's go something crazy at night.
Yeah, there's steam that's coming out. So all of that gas goes in here. We actually have a double connection. So the hot gases then make steam, and we have a steam generator too. But then the hot gases go out into a cooling tower, and it makes a lot of steam. So we see, it looks like smoke, but it's just hot steam. The air comes in, the natural gas burns, the natural gas CO2 and water come out, and then the air, and it's the steam coming from that. So we could see this same shape here at Roans Prairie. So this air intake right here is this piece right here. It's like a big filter, okay? And then the jet engine is right here. And then this exhaust tower looks exactly the same shape as this little drawing that we have here. This is this exhaust tower right here. And then I don't know if there is, but there should be, or could be, a steam generator behind it, okay, that generates more electricity. That would be a second, like a two-stage plant. It might just be a one-stage plant at Roans Prairie. The advantage of these, and we'll get to this in the last part of the course, we're kind of out of time, but the last part of the course we'll talk about how these plants are wonderful because they can be turned on and off on a dime. So whenever cold front comes through and everybody turns on their heaters, this thing can ramp up and meet demand. And then if it's whatever else happens, and wherever everybody's, like my warm front comes through or something like that, then everybody turns off their heaters. Or maybe in the summertime, let's think of that. We've got summertime, it's a heat wave, everybody's AC is going, early in the morning, overnight they like it cold, but at 7 a.m. they turn on the AC and get the curling irons out and the hair dryers, and all of a sudden demand goes through the roof. They can turn this thing on and meet demand, and then later in the evening everybody goes to bed and the demand drops, they can turn this off. And they can run the coal plant and the nuclear plants at their perfect efficiency. And this can go up and down to level it out.
Do factories and jet engines have a way of